Hey guys, welcome to Ovenized. I'm Gregory. In this video, we are going to take a look on a product that a friend of mine and subscriber of the channel sent to the channel. It's a clock distribution system. This is the first version of the device. Look how professional it looks. And this is designed by a subscriber of the channel. Actually, one of the first subscribers here of Ovenized 3 years ago. So the main idea of the device is that we have an Ovenized Crystal Oscillator inside, a modern microcontroller, the ESP microcontroller, Crystal Oscillator is installed here, and we have a clock distribution system, IC, that generates 8 independent clock outputs. When I first got an email about this, I thought that it was a common clock distribution system, but as we have, thinking better today, as we have a very powerful IC here, this is the IC SI5351, as it has this very modern IC, it has an USB port, and as we can change the firmware of the microcontroller, this actually becomes a very powerful signal generator. In the front of the device we have the USB port for configuration, we have the reference in or reference out SMA connector, and we have here a DB09 connector where we power the device, and we have other I/O pins that we can use here available. Here we have 2 LEDs for displaying the status of the device, and on the back we have 8 independent outputs, 8 independent SMA connectors. Really nice form factor here. Let's turn it on. Well, we have 12 volts here, and the oscilloscope is connected to the channel A and channel B of the clock source. Let's turn it on. Yeah, we have current consumption here. The Ovenized Crystal Oscillator is probably heating up now. We're gonna see this current decreasing, slowly decreasing, and we already have output. Look at this beautiful trace, and channel 4 also. Let's enable the 5th on input. Perfect, beautiful signal, and we have 2 10 MHz outputs here with different phases. I'm not sure why the phases are disaligned here, probably a configuration of the IC, and we see that by default we got 10 MHz on the output, channel A, and after channel B, the phase comes different now. That's very interesting. So probably the IC uses different PLLs for each output, and we have a configuration for phase, alignment of phase, or something like that. But okay, we have 10 MHz, very clean signal. I'm very surprised. Yeah, we have a CMOS signal here, and the signal comes pretty fast. Yeah, one channel after the other, probably because the microcontroller is configuring the clock distributor IC channel by channel in the startup. The common usage for this kind of clock distribution system is for synchronizing more than one measurement equipment on the bench in a measurement setup. Or if we have a very precise clock source, frequency source, or time base, as this rubidium clock source here. This is an atomic source that we have here on the lab. We never use it, but I think that now that we have the clock distribution system, it makes a lot of sense to have a very precise and stable unit like this being the reference for the clock distribution, and with the clock distribution system we can spread this clock source around in multiple measurement equipments. This can be used for signal generators when we have more than one signal generator and we need to generate synchronized outputs, and also it is used for acquisition devices where we are sampling a lot of signals, and all this sampling needs to be precise in frequency, sample rate, and also precise in phase. But as I said, looking to the device now, I see much greater opportunities. Probably we can use this device here on the lab as a standalone signal generator. I have been working pretty hard to create picosecond pulse generators for a future video that I'm planning, where we are going to design a ultra-wideband system. Here an example of a transmission line pulsar, another transmission line pulsar, and today this is my best prototype, is a capacitive pulsar that can generate 250 picosecond pulses. So imagine a situation where we have different pulsars, different antennas in an ultra-wideband setup. We can of course use a device like this for generating the transmission pulses. the triggers for the pulse generators. Yeah, okay, I'm very excited with this device here. I hope that it becomes a product, but let's keep going with the video. So for an example of laboratory usage, we have here two signal generators, arbitrary signal generators, and one of the signal generators is generating a pulse waveform and the other one a square wave. I made a setup here with the same frequency, and we can see that we have the two signals being generated. You can imagine any setup that needs more than one signal source. Today we have signal generators that are capable to generate two signals, two channel signal generators. If you have more than two signals, it starts to become complicated. So imagine a situation where we need to generate more than two signals or different formats of signal using different signal generators. The reference source is turned off now, and we can see a very interesting effect on the oscilloscope. We see that the internal sources of the Tektronix signal generators are pretty close. Signal seems to be stable here, but of course, if we zoom on the signal, we're gonna see that, look at this. Of course, the signals are not synchronized because we have two different time bases, one inside of each Tektronix signal generator. So signals look good here, but of course this is not useful for the measurement setup, as actually in practice we have different frequencies, they are not exactly the same, and the phase is being shifted by this offset of frequency. So we first turn on the reference source. Yeah, it's warming up. Let's start to blink, right? And we can change to external and change to external clock reference. And now we see that the signals are exact in sync because the reference source for the two signal generators come from the same crystal oscillator. If we turn off the reference source, let's see what happens. The two signal generators complain that the external clock source is not present. Very nice. What's very powerful about the clock distribution IC that's used here is that we can configure independent output frequencies. So the default is to generate 10 MHz because this is the default for the industry. Clock sources run at 10 MHz. This is a standard, but with the clock distribution IC used here, we can independently generate 8 outputs with different frequencies from 10 kHz to 200 MHz. And this is where this thing starts to behave as a general purpose signal generator. I'm using my computer to record the audio of this video, but I'll try to bring it here so we can configure this device using the serial interface, the USB to serial interface that it has, so we can change the output frequency to see the waveform. Yeah, I hope we still have audio, I think so. So I'm connected through USB to the serial terminal here, and we can see the device booting. Look at this. So I'll turn on the device. Yeah, look at that. Working. Okay. Type help for help. Let's try help here. Oh, I need to turn on the echo. Local echo, right? Help. Yeah, it worked. Syntax set channel power frequency in hertz. So let's try to do here. I will use a notepad, it's easier. So it will be set clock A, comma, power maximum 8, frequency. Let's try 50 MHz. 5th, 1, 2, 3, 1, 2, 3, right? I'm copying this and I'm gonna paste here. Power okay. Frequency. Oh, it worked, look at that. Look at these guys. This is very nice. This is fascinating. Yeah, you can see that they are in sync, of course, because you have multiple PLLs using the same reference source inside the device. Let's try a different frequency. Let's try 75 MHz. I will copy the command, paste here. Unbelievable. Yeah, that's very nice. Look at that. Here we have a sinusoidal signal because we are approaching the limits of the oscilloscope. But I think the signal continues to be a CMOS square wave. Let's go to 1 meg. 1000000. Yeah, copy that. Oh, look at that. This is unbelievable. That's very nice. Guys, I'm very excited because I'm looking forward to have a line of products here, a partnership for the channel. It would be great. I will, of course, talk to this guy to help him to improve the system. Let's get your feedback to see what can be improved here, new ideas, because this really can become a general purpose signal generator. With USB control for automation, this is very, very useful. I'm really amazed by this. A single IC, clock distributor IC, with a very nice case, with an ovenized crystal oscillator, becomes a very, very powerful tool for the lab. So for this last test to verify the waveform, let's see if the edges are clean, what's the rise time of the waveform. I'm connecting the reference source into the Roden-Schwarz oscilloscope because it has 4 GHz bandwidth. Yeah, I turn it on here. Let's turn on the channel. Yeah, the signal is very clean. Let's see here. Very clean signal actually. Transition time is less than 1 nanosecond. We see here. Yeah, guys. This machine here is a very nice machine. I'm very impressed. Well guys, I will be in contact with the creator of this device, trying to bring new ideas. I will give my feedback. I will play around a little more. Please give your ideas, give your feedback on the comments. I really think we can help him create a very, very nice product that can be beneficial for all the all electronics community. I hope you enjoyed this video. Thank you for being here with me, learning electronics together, and I see you in the next video of All Electronics.